All right, folks. Well, here's lecture 10.7 for you about the shape of molecules. So we've looked at so far electron arrangements around certain atoms within a compound, and we've looked at how to draw those Lewis dot structures so that you're showing the electrons for where the atoms are bonded to each other, and you're showing lone pairs if they exist. And so this topic that we're going to look at today, right now, in this video is showing you what shape do these molecules take when you're finally done with that, two-dimensional drawing. Because if you have to remember, these Lewis dot structures that we draw, they're really only two-dimensional. They have a length and a width, so that they fit on a piece of paper, right? Like on a flat piece of paper. But in real life, molecules are three-dimensional. And so what type of shapes do they take? And so you might be scared if you hear the word molecular geometry, but that's kind of what we're looking at, is molecular geometry. But good news is, the only thing you may need to remember is that there's 360 degrees in a circle. If you remember that, then you're good. We're not going to go into a whole lot of shapes or equations or things like that, but there are some things you need to remember. So some rules I'll help you remember or be able to refer to, because if you remember, this test is going to be open book. So, but you still need to be able to refer to this table and know what you're doing so that you can answer these questions. So let's move quick. Follow me here with 10.7. Here's a Lewis dot structure for CO2, carbon dioxide. If you remember, it's got two double bonds there. Now, what you should note is that this geometry here, this linear geometry, is actually due to the repulsion between those two electron groups on the two oxygens. So you see these lone pairs of electrons that are on oxygen. Each oxygen has two lone pairs of electrons. They really don't want to be near each other. Why? Because remember, like charges repel each other. So try to put two negative sides of a magnet next to each other. They are going to be repelled by each other. And so they're going to naturally want to space themselves out as far away from possible, giving you a 180-degree angle here. It's total straight line. This is a linear geometry for CO2. All right, and so what would that look though? What would that look like though for a compound like this, H2CO, where you have two hydrogens and an oxygen connected to a carbon? Well, after you drew its Lewis structure, which hopefully you should be able to do by now, right? This one could be a little bit tricky because you might be tempted to put the hydrogen on this carbon and then putting this hydrogen on that oxygen or something like that. So I would probably have to give you like the skeletal structure for this one, because unless you really knew what you were doing or had done a million of these, this could be a little unintuitive. But if I gave you this skeletal structure, then you would need to put the bonding electrons first, and then the electrons on the terminal atoms, which hydrogens can't hold anymore, right? Then two, so you're good on those. But the oxygen, you'd put those two there, and you realize you would need and you'd have a pair there. You'd realize you need to share some more though with the carbon to give it an octet. So here, everything's got an octet, everything's happy, except for the hydrogens. Obviously, they want duets anyways, not octets. So we have a totally legit Lewis structure. Now what you need to do is figure out its geometry. And the way you do that is you look at how many electron groups are around the central atom. So we're going to be looking at small structures here, not large molecules. But you can kind of, when you look at large molecules anyway, you only look at large molecules by individual regions, called active sites or whatever, on the molecule that are important. And all along the molecule are going to be taking these same basic shapes. There's you'll see there's 1, 2, 3, 4, 5, 6 basic shapes that you can do. You can be, or 5 I should say. You can be bent, tetrahedral, linear, trigonal planar, or trigonal pyramidal. And so how do you get these different shapes? Well, again, the linear is real easy. That's just when you have a 180 bond degree angle when you have two electron groups around the central atom, or two bonding groups, and you have no lone pairs anywhere. Remember, there was no lone pairs on that molecule of the CO2. You didn't see any lone pairs on the carbon, right? And so, wait, yeah, that's right. And so in this case, back up to the H2CO example, we have essentially 3 electron groups. We have this hydrogen here, and this hydrogen here, or this oxygen here, all around a central atom. And so these 3 electron groups want to get as far away from each other as possible. So this drawing is not very accurate because you have a big distance. You have about 180 degree distance here, but yet you have a 90 degree distance there and a 90 degree distance there. So can we space that out a little bit more? Sure. We can spread it a little more evenly so that we have 120 degree bond angles between all of these electron groups. So pretty much assume that this hydrogen is an electron group. The oxygen, anytime you see an atom attached to a central atom, it's basically an electron group because it's going to have some electrons there. So remember, we're concerned with the electrons here. And so this would be a better representation, and this would all be in one plane. So just like you see it on the piece of paper, that's actually how it would look like if you were to lay this flat on if you were to turn this sideways, looking straight at the hydrogens with the oxygen pointing away from you, then it would be like just flat. It would be like it would be in a planar, and it's called trigonal. Like a tri means 3, and so it's a trigonal planar geometry. All right. Now, what if there was 4 electron groups? So a molecule like CH4, super base. That's actually an organic chemistry compound. Methane gas. Has carbon and hydrogen, so it's technically organic. But it is very simple, and it only has 1 carbon along with 4 hydrogens. Remember, carbon wants to bond with 4 different things. That's the maximum things that usually an element will bond with. And carbon, it likes to bond with, it has 4 only valence electrons, and it wants an octet of 8. So it's going to find the fillers, which are usually hydrogens. Hydrogens are great fillers because they come and bring 1 electron. So if you have 4 electron groups like this, you're going to have tetrahedral. So tetra is 4. You're going to have tetrahedral geometry. Now, you're not going to have 120 degrees because of the way these space themselves out. This is actually totally 3D. So you have an up axis, and you kind of have these going down and to the left and down and to the right, or down and away from you. And so basically, if you want to try to get all of these hydrogens as far away from each other as possible, then you're essentially going to have 109.5 degrees between each hydrogen atom. Does that make sense? So between this hydrogen atom and this hydrogen atom, there's 109.5 degrees. because remember, this hydrogen is not only trying to get really far away from this one, but it's also trying to get really far away from this one, and it's trying to get really far away from this one. So they've all taken their place where they're farthest away from each other as possible. Here's a good visual representation of it too. So if you were to draw these lines like this and pretend that they're like lines of an angle, and measure that angle, it would be 109.5 degrees for a tetrahedral molecule. Okay, let's continue on. It gets a little trickier here. Imagine you have 3 atoms like this connected to nitrogen. So you have 3 hydrogens connected to the nitrogen. That kind of looks like this example up here where we had 3 atoms connected to a central atom, but in this case, we also have that lone pair of electrons on the nitrogen. That actually counts as an electron group. Okay, up here we didn't have any lone pairs on the carbon, and on the central atom we didn't have any lone pairs. So we really only had 1, 2, 3 atoms, or 3 electron groups to contend with. And so it's pretty easy to space them out. Here we clearly had 4 atoms, so we clearly have 4 electron groups. But here we have 3 atoms and a lone pair. We have to treat that lone pair as though it was an electron group, just like these atoms. And so we still have sort of a tetrahedral arrangement, but In this case, it's going to look like a pyramid, and if you were to just look at the atoms, you would see the 3 hydrogens poking down, but you wouldn't see any atoms up here. All you would see is a lone pair. Well, when we draw the structures, we put together those like ball and stick models, we generally don't have a hole to put lone pairs. Like we only are showing connections between atoms. And so you end up with this kind of pyramid shape, and it's called trigonal pyramidal. It's a little bit different than the trigonal planar because all of this is in one plane. If you were to turn this sideways, it would be just like you're looking through one flat plane. But here, you're not looking through a flat plane because the nitrogen is sort of elevated higher than the hydrogens, isn't it? And why is that? What's pushing the hydrogens down? It's this lone pair up here. This lone pair exerts a repulsive force against these hydrogen atoms because it's electrons against electrons. So this lone pair is actually pushing those hydrogens down. And so if you were to look at the ball and stick model, it would look like this. That's called trigonal pyramidal. And so the way to remember that is when you have 3 atoms or 3 bonding atoms, but yet 4 electron groups. So when we go back to our table, because this is kind of going to have to be the master table that you'd learn how to use. The way to use this table is you look at how many electron groups there are, how many bonding groups there are, and how many lone pairs there are on the central atom. And then here, this will be your electron geometry. Here's the angles in between, and this is the name of the molecular geometry. This is the answer. Usually I ask you about the molecular geometry. And then these are examples as Lewis structures and examples as ball and stick models. And so again, the trigonal pyramidal, the one we just looked at, is this one here. It's got 4 electron groups. But only 3 of them are bonding groups. One of them was a lone pair. And so you have essentially a tetrahedral electron geometry. So it's tetrahedral like this. You have something poking up over and over. So you have 4 different, it kind of looks like a tetrahedral like this, but yet one of the atoms is replaced with a lone pair. But if we wanted to talk about its electron geometry, we would say it's tetrahedral. But that's not really what the answer is. The answer is what is its molecular geometry? Well, because one of them is a lone pair, again, it's pushing down on the 3 atoms, and it's really going to have a trigonal pyramidal molecular geometry. All right. So you have to use that table essentially. Let's look at another example. Let's look at water, a real basic example here. Again, doesn't everything have a tetrahedral pretty much? No. Nope. Not all electron geometries are tetrahedral. Most of them are. These 3 down here are. But some of them, you only have so many electron groups. Everything, a lone pair or an atom, both count as electron groups. But lone pairs are different than bonding groups. So these are different. Basically, the bonding groups and the lone pairs should always add up to how many electron groups you have. Right? Okay, so we look at water again. It has a really easy bent structure, but how do we get that bent structure? Well, again, let's look at the Lewis structure first. The Lewis structure has the 2 hydrogens, first of all, that are bonding pairs or bonding groups. You have an electron group there that's participating in a bond. You have an electron group here participating in a bond. But then you have an electron group here that is just a lone pair. You have an electron group here that is a lone pair. So you essentially have 1, 2, 3, 4 electron groups. So you have this tetrahedral electron geometry where there's 1, 2, 3, 4 groups of electrons, but 2 of them are bonding groups of electrons there participating in the bond represented by the line, but the other 2 are lone pair groups, one up here and one down here. And really what's going to want to happen is those electron groups will actually be at both up here at the top, pushing down on the hydrogens, making them Because see, technically, if you were to like rotate this a little bit, like push this forward, have this come up a little bit, then you would see what I mean. This is hard to do on a two-dimensional piece of paper, really. But basically, both these lone pairs are pushing against the hydrogens, and they're pushing them down like this, so that the hydrogens are sort of like on the same side of the water molecule. And then up here are lone pairs that you just don't see, but they're really there. There's a pair here and a pair here of electrons pushing down on the hydrogens. And that is giving it a bent shape. We just call it bent. All right? And that would be when you have 4 electron groups, but 2 of them are bonding groups and 2 of them are lone pairs. And the angle between them is still 109.5. So have we covered, that pretty much covers all the examples, right? Pretty much. There is this example here, trigonal. If you have something that has 3 electron groups like this molecule here, you have a lone pair, you have an oxygen and an oxygen. So you essentially have 3 electron groups, but only 2 of them are bonding groups participating in the oxygens, and then only 1 of them is a lone pair. This double bond here, you pretty much just treat it as one bonding group. Don't treat double bonds as though they're like 2 groups for each double bond. No, the fact that you have a connection here just counts as a bonding group. So you have a bonding group and a lone pair. So 2 bonding groups and 1 lone pair for a total of 3 electron groups will give you this bent shape, because the lone pair that's technically right here is pushing down on these electrons that are on the oxygens, giving you a bent shape, kind of like the water molecule, but a little bit different bent shape. You actually still have 120 degrees here, kind of like the trigonal planar, where you have 120 degrees, 120 and 120. This is 120. Whereas the water molecule, this angle is a little bit less than 120 because you have not one, but 2 electron pairs pushing down on the hydrogens. So you have a little bit of extra electron force up here pushing down on the hydrogens, where on this molecule, you only have 1 lone pair of electrons pushing down on those oxygens. So it's a little weaker. But if you can push these hydrogens down further by using 2 electron pairs up here, that you have that group, you have that lone pair and that lone pair. If both of those are pushing down on the hydrogens, then they push the hydrogens even closer together, making a smaller angle there at 109.5. Okay, so looking at some, this is actually called, it has a name, by the way. It's called the VSEPR theory. It's called the valence shell electron repulsion theory. Actually, let me just double check that. It's called the valence shell electron pair repulsion theory. It basically says that electrons are repulsed by each other. They're going to repel each other. And so that theory leads us to this assumption that the molecules take these shapes, and we verified it through other scientific experiments that it is true. Okay, how about this molecule? You know, again, the way you do these, you're always going to have to start by drawing an accurate Lewis structure. So if you were to draw the Lewis structure for phosphorus trichloride, you add up all the valence electrons for phosphorus and 3 chlorines, you end up with 26 electrons. You show the bonding pairs first, and then you show the other ones around the terminal atoms, or the outside atoms, trying to form as many octets as possible. And then you stick, if you have any other remaining ones, on the central atom, which we do. We end up putting a lone pair there, don't we? And so we're all done with our structure. We have all electrons accounted for, no extra, no less. We don't have any double bonds or anything like that here, do we? We're good. But basically, we have how many things around the central atom? We have 4 things, right? We have 3 atoms and 1 lone pair. So what's going to happen? Well, you're going to have you have 4 things around the atom, 4 total things. So you have a tetrahedral like electron geometry, but only 3 of them are atoms. 1 of them is a lone pair. So you just go up to your table and you see, where do I have 3 bonding groups but 1 lone pair, where there's 4 electron groups total? That's right here. So you're going to have the answer again is not right here. Don't look for the electron geometry. That's just the electron geometry. But what is the real molecular geometry? It's trigonal pyramidal. Trigonal pyramidal would be the molecular geometry. Unless they ask you for the electron geometry. If they ask you for, usually they ask you for both, I think, in the homework. And the molecular geometry, yes, is trigonal pyramidal. They asked for both, didn't they? All right, what about this example here, a nitrate ion? Now, this is a good example because the fact that it's a negatively charged ion hopefully reminds you that you have to add one more electron to the total. So nitrogen has 5, oxygen's at 6 apiece. There's 3 of them, so that's 18 plus 5 is 23, plus another to be 24. So showing all 24 electrons, showing the bonding pairs first, and then the terminal atoms, and then we run out, but then we need an extra pair there on the nitrogen to give it an octet, because technically everything needs an octet. We have to borrow from this oxygen. Now, we could have borrowed from this oxygen too, couldn't we have? Or we could have borrowed from this oxygen. So technically this is a resonance structure. There's actually 3 resonance structures for a nitrate. You can have a double bond there, you can have a double bond there, or you could have a double bond there. But either way, if we're just trying to figure out the geometry right now, all we're concerned with is the fact that we got how many things around the central atom. You got 1, 2, 3. Because we don't have a lone pair there on the nitrogen anymore, do we? So we technically just have 3 things. 3 groups, 3 atoms, or 3 bonding groups. So 3 and 3, where's that? Right here. 3 electron groups, and all 3 of them are bonding groups. We have no lone pairs. That's going to be a trigonal planar. Electron geometry and a trigonal planar molecular geometry. They're the same. All right. There you have it. So pretty simple. You basically just have to learn how to use that table. I really don't know why they went into, yeah, I do. This is awesome. Please pay attention to this, especially if you're going into, because a lot of you guys could end up in my organic chemistry or biochemistry class next year, and this is something that's very important. We can't draw 3D stuff on 2D very well, so we make the drawings a little more complex. Instead of just drawing a straight line, which sometimes we do, if the bond is literally in the plane of the paper, we just draw a straight line. But if we want to represent a bond that's like going away from us, technically, like into the paper, if you will, like away from you, you use like a dashed line. It's like dashes. It's kind of like a triangle, but yet it's like dashed or hashed, however you want to say it. If you want to represent a bond that's like coming out at you, like it's literally leaving the paper and projecting towards you, the bond is literally projecting out and towards you, then you would use a wedge. So it's all like dark. It's wedge. It's not hashed. Does that make sense? So that way, when you look at structures like this, then it's clear. Like here's a tetrahedral. Okay, these two are just in the plane of the paper, but this X is technically like going away from us right now and going further into the page, and this X is actually coming closer to us. And that's how we end up with that tetrahedral shape, so that you can almost like visualize it in your mind. Here's a bent shape where both of them are in the plane of the page, right? Here's a trigonal pyramidal where actually one is going away, one is coming out at us, and one bond is just in the plane of the paper. Here's a trigonal planar representing that all of the bonds are in the plane of the paper, because remember, that's what planar means. It's all in one plane. There is no up or down from this arrangement here. Linear is the same way. It can all be in the plane of the page. Okay, that's it. Wow, that was actually kind of quick. The next lesson's on electronegativity, and which is very important as well. Extremely important, actually. Let me switch camera angles there. And so if you have any more questions on the shape of molecules, there's another good tutorial I can show you on YouTube. The Tyler Do It, he has a really good one. Or chime into my Zooms and I can help you with specific problems. But you'll have some of those to answer on the test, so be ready for that. Adios.